Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be looking at Chapter 6, which discusses Observational Studies, where we will learn about adjusting for things that you cannot control. So when we looked at doing experimental designs, our motto was block what you can and randomize the rest. Here, with observational studies, you no longer have the control of imposing a treatment on observational units to observe a response. Instead, you simply observe what you can about objects in nature, and then you learn what you can from that. And adjusting for what you can't control is the major theme of this chapter. So, in most scientific studies, the groups being compared do not consist of identical experimental units that have been randomly assigned to receive a treatment. Okay, groups may be extremely heterogeneous, which means that, say, a smoking group and a non-smoking group, if you want to know if smoking has an effect on some health outcome, smoking is related with other behaviors, and so it's not like we have got two groups of identical people, but the only difference between them is smoking. There's lots of other potential factors that are different, and so those are the factors on which that the groups are heterogeneous on, and that you want to control for. And in fact, all those factors may all be related to the specific response on which you want to compare the groups. So that's what makes observational studies challenging, is that you are observing groups, you want to make a comparison, but the groups are different in more than one way. And that's where problems can happen if you ignore those differences. So the following problem emphasizes the care that you need in an observational study, and we'll see why LS means is the appropriate way to make comparisons rather than grand means. And even though these data are artificial, representing something called Simpsons Paradox, something we've looked at last semester briefly, they are consistent with data that were collected in a real data scenario. So here's our situation. In 1970, we sampled high school seniors, 550 of them, and then 20 years later, in 1990, we had another sample of 550, and we observed the SAT score for those students. So we'll take a look at the plot of the data. So on the left we have 1970, on the right we have 1990, and we have their score on the SAT on the vertical axis. And we see sort of slightly unusual distributions, but the period, the big dot here, represents the grand mean of all the observations. And you can see that over time, from 1970 to 1990, there's a decrease in about, 15, 20 points in the SAT scores. And so just based on the marginal summary, you might be concerned that SAT scores have been going down over this 2-decade period. Of course, there's lots of context which is missing from here, right? We don't know very much about any of these points. We don't know about any of the years in between. Just a gross comparison between students 2 decades apart. Okay, so as I mentioned, here's some numbers. We've got the SAT scores differ by about 10 points, and they decrease over that period of time. So that would be the conclusion. If you put this right into a linear model, okay, so grades is the response by year, which is categorical, and you make a comparison, there's a difference in years, and when you calculate the means, here they are, 10 points difference. And if you use LS means to calculate confidence intervals for each year, as well as do a contrast, you see a difference of 10 with a small standard error of 1.3 is highly significant. So, should we be alarmed that students are doing worse than they were doing 20 years ago? So actually, without going any further, I might not necessarily be concerned, because even as students improve, the SAT gets, probably keeps up with students improving too. So you'd sort of expect students to basically perform as well from year to year if the test is keeping up with the skills of the students. Okay. And I've got some other comments here, but I'll skip those. You're welcome to read them. All right. But this is an observational study, and we have two distinct populations, one from 1970, one from 1990. And things can change, right? I moved in 20 years, and I've somehow changed a little bit the demographics of both New Hampshire and New Mexico by doing that. So it turns out that there's another variable in this data, in particular, in this case, ethnic groups, which are just numbered 1 and 2. And this hypothetical data that doesn't really mean anything. Okay, it could have been anything else. But in this case, the ethnicity makes a difference. So if I zoom in on this table, we see in 1970, the ethnic group 1 was started at about 900. And in 1990, ethnic group went up to about 950. Similarly, in 1970, ethnic group 2 started around 825, and in 1990 went up to 875. So if we look at this by group, it looks like both groups have improved by about 50 points each. Oops, too much. All right, let's take a look at this plot. So here's when we control for ethnic group, by including it as another variable in the plot, we see what that strange structure in the plot was. It turns out that both ethnic groups have increased actually by 50 points. The grand mean has decreased by 10, but that's because of a large offset in sample size relative to the signal within each group. And that so-called paradox is called Simpsons Paradox. How the grand mean can behave in a different direction than separate subgroup means. So if you include the ethnicity as a factor in the model, so here we've got age by ethnicity. This multiplication sign says we've got main effects for year, ethnicity, as well as the interaction. And look at the main effects, we find in fact that there isn't really much evidence for an interaction, but there is main effects for both year and ethnicity. And that's supported by the parallel lines that we see in this plot. So interaction would indicate that there is non-parallel lines. Okay, so I'm scrolling back down. We can use Plier to calculate some of the means. Let me just scroll through some of this, and I want to point out the pairwise comparisons of the years for each ethnicity. So we find that for ethnicity 1, from 1970 to 1990, okay, so it's 1970 minus 1990 in that order, because 1990 had a higher score for ethnicity 1, this estimate is negative. Okay, so this represents actually a 48-point increase. Same thing here for ethnicity 2. And because there was no interaction, if I scroll back up, we can look actually at the LS means just by ethnicity. So there's a difference in ethnicities of 74 points. But more interestingly is that by year, the difference in years was about 50 points for each ethnicity. Okay. And note there is a comment down here. Results are averaged over the levels of ethnicity. And, okay. Interesting. This note here is important, but we can ignore it. So we fit a model. I'll scroll up for a moment. We fit a model that has the interaction included. Okay? And if I scroll down for a moment, we have the interaction in the model, which is not significant at a 0.05 level. And the thing probably to do at this point is to simplify our model and change this to a plus sign to only include the two main effects. In that case, the modeling only has main effects, and when we look at the ALS means for a marginal effect, for example, just year, not conditional on ethnicity, then it won't give this warning. Okay, so this warning is important. It's not. It's dangerous to look at marginal effects such as only year if there's an interaction, if the effect of year depends on which ethnicity you're in. Okay, so I'll scroll back down. All right, so there's lots of discussion here that is worth reading on your own. And the important closing here is that this idea of controlling for the things you can't control, let me rephrase that, adjusting for the things you can't control, meaning we can't control the density of ethnicity in our sample of SAT students. So we should include ethnicity in the model. We should also include sex and age and any other factor that potentially has influence on SAT scores. We may find that many of those factors don't have predictive ability for the SAT score over and above other factors, and so we can actually simplify our model somewhat. But the point is that if you miss an important confounding variable in your analysis, you can really be misled. And the degree of being misled can be, it typically isn't as big as this, going from a decrease of 10 points overall to an increase of 50 points within each group. But it can still be wrong enough that you miss important features in the data. So adjust for what you can't control, and do this whether you're doing controlled experiments or observational studies.